Welcome to my this tutorial sessions. Okay, so this is your tutorial 9. Okay, tutorial 9. Okay, in my previous live session I gave you one homework. So anyone have tried that problem? Please respond. Yeah, I'm repeating the question again. 1 minute. Your question was yeah, this was the question. So let t from V to V, okay, be a linear map, okay, such that image of t equal to kernel of t, okay, what can you say about t square? Yeah, please tell. So t is a one linear map from V to V, okay, such that image of t and kernel of t both are same. Then what we can say about t square? At first, please tell me, can you give me one example of linear transformations? Take V's and R2 from R2 to R2 such that satisfy this condition that image of T and kernel of T are both are same. At first, please give me one example of such linear map. Then you can feel the problem, I think. T square equal 0, okay, how? Vishal, please on your microphone and tell.
Sir, Txy equal to 0, 0.
Tx
T operated on xy and it gives us 0, 0 in R2.
you are taking this one. T is map from R2 to R2. You are taking T of xy goes to 0. This one are you talking about, Rajesh?
Yes, sir.
But
Yes, sir.
what is the kernel of T here? Kernel of T is whole R2. But image of T is only this one. This set. These two are not same. Vishal, can you please tell me how did you get that t square equal to 0?
Sir, can you take identity map?
Identity map, that time your image T is full R2, but kernel of T is 0.
Okay.
Yeah. So this will not be work. Identity also will not be work. We already know. If we know the image of linear transformation on basis, then we done. So try to think about take basis and try to act linear transformation on basis to get some image. Okay, then I think it will be very easy. Construction in general form is sometimes a little bit difficult. Try to think about on basis. Okay, so this is R2 to you need a linear transformation from R2 to R2. What is the basis of R2? Yeah, please tell what is the basis of R2. Hmm?
Sir, standard basis.
Yeah, take 1001. So if we know that one linear transformation on these two elements, then we done. Okay, so try to construct one linear transformation from R2 to R2. We need that image of T and kernel of T are same. Okay, so you have to observe one thing. If kernel of T 0, observation. Okay, if cut T equal to 0, then T is a 1 1, means since these two are dimension are same, T is on 2 also. Okay, so that time we will get image of T is full R2. Is it okay or not? Is it
Yes,
fine?
sir.
Everyone agree with this statement? Hans?
So,
Yes,
sir,
sir.
can you take T from 01 and 102 and flip other side that element, like T E1 E2 to E2 E1?
You are telling like that. This is goes to your 0 1 and this is goes to your 1 0. Like that.
Yes, sir. Yes, sir.
Okay, please wait. So if your observation is, so one layer transformation will satisfy this one. Okay, so we take the domain is R2 and R2 such that image of T equal to kernel of T. We need this linear transformations. Okay, before that here I am writing some observations. Okay, so if your kernel of T is 0, then what we are getting, image of T equal to R2. Is it fine? Please tell me at first. Are you agree with this?
Yes. Yes, sir.
Okay, so here kernel of T is not equal to image of T. Okay, so you can take T is a bijection map. Okay, so you can take both. You can take kernel of T equal to 0 or image of T equal to R2 you can take. Okay, so if image of T equal to R2, then otherwise you will get a kernel of T equal to 0. Okay, if this one, then you will get that kernel of T equal to 0 for if both the dimension are same that time. Okay, otherwise we will not get. In previous my lecture I gave example. Okay, so these two are if and only condition. So you can't take this one, because if you take this one, uh, your e1 goes to e2 and e2 goes to e1, that time you are getting that image of t is full R2. That time we will get kernel of t equal to 0. So that time these two will not match. Okay, that time we will not get this one. You will get not equal to. Okay. So you can't
Yes, sir.
take the zero map and identity map or any bijection map. Okay. So you have to think other way. Yeah, we are try to think it's almost, yeah, this approach is almost going to our answer. Yeah, two bases is this one. Yeah, we need one non-trivial kernel. Okay, so non-zero kernel we need. This is your first aim. You need one non-zero kernel. So one of the basis elements goes to 0. Then we can get a non-zero kernel. Understand? Could you understand my statement? My statement is like that. One of the basis element have to goes to 0. Are you agree?
Yes, sir.
So which one have, so yeah, and we another way we need kernel of t equal to image of t. So which basis if you send to 0 will get the required Linear transformations. So getting non-zero kernel, we are one of the bases have 2 goes to 0. Okay, 0 element of R2, one of the basis element. This is, otherwise we will not get the kernel of t equal to 0 if both are goes to non-zero. Okay, so that time we will not get that kernel of t equal to 0. Okay, so one of it have to goes to 0 and other one you can send to another way. So please tell me which one the your good choice. You can send this one to 0 or this one can be 0. Okay, so I am sending this one to 0. So please tell me where I have to send this one. What is the choice for this one? Then we will get image of t equal to kernel of t. Okay, so if I send, sorry,
Sir, 210,
yes,
210.
yes, because from here we are getting that kernel of t is generated by this one. If we send this one to 0 0, then we will get kernel of t is generated by 10. Okay, so we need image of t equal to this one generated by this one, so we need this one. So only choice is we have to send this one to 10. So this is your one example. Okay, of one example, one data transfer from R2 to R2 which satisfy this one, the image of t equal to kernel of t. Okay, so please tell me what is the property of this map. After that we will go for general proof.
Sir, it's a reflective map, na? मतलब reflective, the 0 1 and 10 are reflective, na?
How what do you mean by reflection? Reflection, I'll go to reflection, rotation, everything. Reflection means you have one xy. Okay, so in three way we can think about reflection. One is on x-axis, one is on y-axis, one is any line going through origin. Okay, so if you take reflection on this one, will this will come
Oh,
your opposite direction here. in on
Yes, sir.
y,
They are not.
this is
They
not a
are not. They are
reflection.
not.
Yeah. So what we can say about t square for this map? Our question was, if T is a linear transformations on V such that image of T and connected T both are same, what can we say about T square? This is one example we are getting here. Okay. So what can we say about T square? Yeah, this is your T. Okay. Yeah. So T square means, so at first we will go R2 to R2, then we will go to R2 to R2. Okay. This is a composition. T compose T. Okay. What can we say about this map for this example? At first, please tell me, for this example, what is the T square? What is your T square? So
Sir, 0 0, sir. 0 0. Sir,
how
0, comma. Sir, same like kernel T. 1, comma 0.
T square equal to, or take
Sir, 1 0 0, no, sir.
take this one, x comma y. So what we will get?
Sir, 0, comma x.
Or 1 minute, or we can
Sir, T
huh?
goes to 0, comma x.
T goes T goes to means, yeah. So we are, please look on what is the image of this one. We will get T of 1 0. T of 1 0 goes to 0 0. Okay. So we are getting T of 0. This is equal to your 0 0 in R2. Okay. And what is the image of this one? 0 1.
0 0.
Yes, for this one is also we will get T of 1 0. Okay. Then we will get again 0 0. So we are here, we can observe that T square acting on 1 0 is goes to 0 0. T square acting on 0 1 is also goes to 0 0. So in basis we are getting T square equal to 0 for so in general we can tell that for all x y belongs to R2, T square x comma y equal to 0 0 means T square equal to 0 on your R2. Okay. So can you give me the general proof for arbitrary vector space? This is the particular one example. Okay. This is for this example. This satisfies that t square equal to 0. So this is one opportunity, or this is one advantage you are getting from your this example. So this t square might be 0 for this under these conditions. Okay. So answer is also t square will be 0. So how we can proceed? How we can proceed? Yeah. So this is one transformation is given. Okay. Your v to v such that image of t equal to cut t. Okay. This information is given to you. Okay. So this is your v, this is your v, this is your also v. So this is t. Okay. This is second time. Okay. Okay. So take any arbitrary element from v. Okay. So what is the image of this one? Yeah, please tell. Yeah. So we can write this is as like that. Can we write? This is correct?
Yes, sir, correct.
Okay, so this is the belongs to your image of T. This one, this element only is belongs to your image of T. Is it fine?
Yes, sir.
Okay, so T of xy belongs to your image of T, and we already know that image of T equal to kernel of T. So what we'll get? This element T of x comma y belongs to your cut T. Cut T means, what is the meaning of kernel of T?
Sir, those elements who map to zeros of codomain
Yes.
elements
So
with
when we'll
codomain
acting
element.
again, when we'll acting T on this element, we'll get 0.
Zero, yes, sir.
We'll get 0. Okay, on V. We can write like that, on V. Okay, then what we'll get? This is the 0 element on V. Okay.
Yes, sir.
Yeah. So your T square equal to, this is true for all xy. Okay. Sorry, no, don't take xy, uh, because this is, we don't know what is the dimension of V. Okay, take arbitrary x only. Okay, sorry, this little mistake is there. Take one arbitrary x. Okay, for all x belongs to V. Okay, so T of x belongs to image of T. Okay, and these two are equal. So what we will get? T of x belongs to kernel of T, then we will ultimately will get this one. Okay, because we don't know what is the dimension of V, so take arbitrary x belongs to V. Okay, is it fine?
Yes, sir. It's like constant net, sir. Like
Yes,
each
yeah,
element of
for
yeah.
T square, not in T. In T square is
Yes, sir.
goes to 0 map only.
Okay,
Okay,
sir.
so this is the one property. If if one linear transformation satisfy this condition, that time we'll get that T square equal to 0. Okay, oh my god. Yeah. So yeah, Roby was talking about reflection something, so I am going to that. Okay, so geometric transformation. Before that, I want to mention something. Mm, yeah, so suppose everyone, I think familiar with matrix. Okay,
Yes, sir.
okay. So suppose I am only considering only, okay, take arbitrary matrix. Okay, take A is an m by n matrix. Okay, m is row and n is your column. Okay, and I am defining one linear transformations. Okay, from where to where? Here m cross n matrix. So I want to define a linear transformation from where to where? Rn to Rn. Okay, how we can define? We can define x such that Ax for all x belongs to Rn. This is your given matrix. Okay, I am define one transformation, one map. Okay, one map from Rn to Rm such that T of x equal to x. So one can verify that this T is a linear map. one can verify this one. So I am not going to that verification or everything. Okay, so for your kind information I am, yeah, mentioning all those things. So if you have one matrix, okay, arbitrary order matrix, okay, so we can, someone can define one map from Rn to Rm. Why you are taking Rn? Because we have to satisfy the matrix multiplications. Okay, this is your m row and n column. Okay, so for satisfying matrix multiplication we need the transformation from one map from Rn to Rm. Okay, we can define Tx equal to A into X. So, one can verify that T is a linear transformations on Rn to Rm. Okay, or from Rn to Rm, whatever. Okay, leave it, this one. Okay, on linear transformations. Okay, so and someone can define this map, someone can denote this map like this one. If you want, you can denote this linear transformations like that. Okay, here your A is fixed, corresponding to fixed matrix we are getting one linear transformations. So my question is reverse. Okay, so suppose you have one linear transformations from Rn to Rm. This is given. Here our matrix was given, we got one linear transformations. Here your linear transformation is given. So can we get one matrix such that T of x equal to x? Can we get this matrix? Here your matrix was given, we define one map from Rn to Rm such that Tx equal to Ax. That time we can verify that is a linear transformation, and we can define, sorry, we can denote this map like that. Okay, okay, so my question is reverse. One linear transformation is given. Can we every time can we get a matrix such that we can represent linear transformation like that? What is your answer?
Yes, sir.
Yeah, so all time we are getting. So if one linear transformation is there, we can think it as a matrix. If matrix is given, we can think it as a linear transformation. So every linear transformation can be written as, or every linear transformation, for every linear transformation there is a unique matrix such that we are, sorry, 1 minute. Okay, so do you have one linear transformation? Corresponding linear transformation, we will get one matrix such that T of x equal to x, and if you have one matrix we can get a linear transformations. So sometime sometime one problem is given for a matrix. Okay, find this one, this one, this 40, this 40. So that time we can convert matrix to a linear transformations. Okay, and we can check for that. Okay, and sometime it is easy to verify. Suppose someone are asking some property or some problem on linear transformation. Sometimes is it sometimes it is easy to verify for matrix. So for every case you can transfer linear transformation to matrix and matrix to linear transformation for solving your problem. Okay, so sometimes it is easy for transformation, so you can transfer matrix to linear transformation. Sometimes it is easy to think about matrix, so that time you can go to linear transformation to matrix. Okay, so depend on problem you can convert it on, depend on your situations. Okay, so you anytime you can think linear transformation as a matrix, matrix as a linear transformations. Okay, so this is now I am going to some geometric transformations. Okay,
Sir, that's mean is linear transformation associated with a unique matrix?
yes, unique matrix, yeah,
Okay.
and all property will be preserved. Suppose linear transformation has some property, this will preserve by this matrix also, and some matrix has some property, this will preserved by this linear transform corresponding linear transformations. Okay, we can tell that A is a corresponding matrix of the one given linear transformation, or in other way we can say that, yeah, uh, T is a T is a corresponding linear transformation of A. Okay, it's a corresponding associate
Okay,
with
sir.
matrix. Yeah, these two are unique. Corresponding one matrix will get one unique linear transformation. A corresponding one linear transformation will get one unique matrix. Okay, so and both property are same. They will preserve same property. Okay. Okay, so now I'm going to some geometric transformations. Geometric transformation. Okay. Okay. So first I will start with reflection. So yeah, Robbie was talking about reflection operator. Okay. Reflection map. How looks like a reflection map? What do you mean reflection? Please tell me at first. So I am talking about only R2. Okay. Yeah, on transformation on R2. So this is your R2, this is one map. One point is here, X and Y. So at first, what do you mean reflection? Please tell me. What is the reflection?
So, sir, mirror image.
Yes.
Like XY, if on the origin we put a mirror, we'll get minus X minus Y on the third quadrant.
Yeah. So mirror with respect. So if you have mirror in front, okay, then this is respect. If mirror is here, then we'll get reflection of that, but in that portion, not your front portions. Okay. So depend on where we needs our needs. So at first I am talking about reflection on x-axis. Okay, reflection on x-axis. Okay, this is your x-axis. We are talking about reflection with respect to x-axis. So okay, so yeah, we'll get here. Yeah, this is your point. Okay, so what is the point here? Minus x comma y.
X, sir, X comma minus Y.
Okay,
Yes, sir.
fine.
X comma minus Y.
Okay, yeah. X comma minus y. Yes. This is your x comma minus y. Okay. So please tell me what is the transformation and what is the corresponding matrix is. Transformation is your t comma xy is goes to x comma minus y. Okay. So this is your linear transformation. So what is the corresponding matrix we will get for this map? What is the
Sir, 1 0 0 minus 1.
So we are talking about 1 0 0 minus 1, this one.
Yes, sir.
Yes. So how did you get this one? If you are familiar with that, suppose one transformation is given, how to get the matrix? Rajesh? Everyone
Not quite sure, sir.
No, everyone are familiar with, suppose one transformation is given, how to get the matrix corresponding that linear transformations. Do you have any idea?
No, sir.
Robi?
Sir, once recap कर दीजिए. Once recap, sir, how to get it.
Okay.
Sir, the transformation, how to get it, sir?
From transformation to matrix. Okay.
Yes, sir. Both way, from matrix to transformation or from
No,
transformation to
matrix
matrix.
transformation is very easy. Matrix to transformation, you are multiply with vector, then we'll get
Yes,
the
sir.
transformation.
Yeah.
Yeah, it's
The,
it's very easy. Yeah. So I at first I told this one, it is very easy. So other way, this is the converse part. If you have transformation, how will get that matrix? Okay. So I am talking about R2. You can extend it for Rn. No issue. It is very easy. So I am talking about only this one. Okay. So at first write it as a basis. Okay. So one can write. Are you agree with me?
yes, sir.
Okay. And this one, 0 minus y into, oh sorry, you take, here I am taking plus. Okay.
Yes, sir.
So here we can think like that. That transformation is goes to 1 0. Okay. And our this one is goes to 0 1. Okay. Okay.
Yes, sir.
Yeah. So this is your map. Yeah. Take, this is your first column, this is your second column. I think you, I still you are not convenient, is it? Are you feeling comfortable or you need
Sir, sir, here basis we could easily find, but in at certain equation we can't easily get the base, no?
no, every time you can, the basis is for Rn you can test standard basis you can take, no issue. So what is the aim I am telling about? Okay. So take one. For Rn, okay, Rn to Rm, okay, take x belongs to Rn, okay, then we can write it as a linear combination of your basis, okay, alpha I ei, okay, alpha I belongs to R, is it?
Yes, sir.
Yeah, take this map, what will get? We will
Sir,
get alpha I,
sigma alpha I T ei.
yes, this one, okay. So we need only this one, that what is the image of T of ei, then we done. Okay. So if we get this one, that time we have to, like that, we have to retain this one as a linear combination of again your ei, that after that we will get the matrix form. Okay.
Okay, sir.
I think you are not, I, it is little bit not difficult, but you have to go through proper example or proper construction. Okay. So here I am telling properly to you, yeah, for this example. Okay. So here T of 1 0 is goes to 1 0, and 0 1 is goes to where? 0 minus 1. Okay. So it is, we can be written as 1 into 1 0 plus 0 into 0 1. Okay. It can be written as 0 into 1 0 minus 1 into 0 1. For this one also you have to, you will get that T of ES goes to somewhat image of this one. You have to again, you have to you have to rewrite this one as a linear combination of ei. Here I am writing, this is your image of 1 0 is this one. I am writing this as 1 into this one, 0 into this one, okay, and here I am writing 0 into this one and minus 1 into this one. What will be your matrix? Your matrix will be, okay, this is for coefficient corresponding 1 0. Here I will take coefficient corresponding 0 1. What is the coefficient corresponding 1 0? 1 and 0, 1 and 0, and here 0 and minus 1. This is, okay, then rewrite this one. This is your matrix A, okay. Is it fine? Or take
Yes,
this
sir.
one. Yeah, I am telling about this is, take 1 0 equal goes to your 1 2, t of 0 1 goes to your 2 3. Yeah, so how we can write this one? We can write 1 into 0. Is it fine? Yeah, we can write this one.
Yes, sir.
Yeah, then what will be A? Please tell me. What will be A? This is a coefficient. I am taking a coefficient of 1 0. So 1 2, your first column. Coefficient of 0 0 1 is 2 3. This is your. We can verify also. Take 1 0. A into 1 0. How? What will get? We have to get the first column. Okay, 1 2 2 3. Multiply with this one. I think will, yeah, this is your first column, okay, and 0 we can verify that we will get this one. Did you get it? How I am getting the matrix A?
Yes,
Please,
sir.
Rajesh, are you comfortable with this one?
Yes, yes, sir. Yes, sir.
So what is our aim? Our aim, we are getting some image of this one something and image of this one something. So we have to rewrite 1 2 as a linear combination of standard basis of R2, and again we have to rewrite this is a standard basis of R2. Then we will get the matrix A with respect to, this is a very important, with respect to standard basis, STAN, standard basis. If someone change the basis, R2 have infinitely many bases is there for R2. So here I am considering only standard basis. If someone change the basis, if someone tell you please find a matrix of this linear transform with respect to this basis, if someone mention that basis, then we have to rewrite this one as a linear combination of those bases, and this also you have to rewrite this one as a linear combination of those bases. If someone change the basis, okay, that time we will get the different matrix. Understood?
Yes, sir.
Yeah, that time we, suppose someone change this 1 0, we, the basis we are taking this basis, okay. Suppose someone can take this one as a basis of R2, someone can, because these two are linearly independent, we can take. So that time we have to write 1 2 is like that. How we can write? We can write, okay, minus 1 into 1 0 plus 2 into this one. That time we have to write this one as a linear combination of this one, okay.
Yes, sir.
Yes, sir.
Yeah,
Correct, sir.
yeah. So don't think about that, only for your convenient take all time or standard basis, okay. If in problem they mention something, then you have to change regarding those basis, okay. Otherwise all time take standard basis, no issue. So what, so this is your linear transformations, this is your matrix when we are getting the reflection on x axis. Then what will the matrix when we will get reflection on y-axis, what will be the matrix? Yeah, here. Okay, reflection on y-axis.
Minus x comma y.
Yeah, then what will be your matrix? Please tell.
Sir, minus 1, 0, 0, 1.
Yes. Okay. My next question is interesting. Reflection on your any line passing through origin. On a line, okay, passing through origin. Passing through origin. Please tell me this one. Try to draw the picture and please give me the answer.
Sir, minus 1, 0, 0 comma minus 1.
You are telling about. Please tell.
Minus 1, 0, 0 comma minus 1.
Minus 1 0.
0 comma minus 1.
Yeah. What is the transformation? Please tell me at first.
Sir, minus x comma minus y. Minus x minus y.
1 minute. So this is your x-axis. So you are taking this line. Is it?
Yes, sir. Oh,
Yeah.
no,
That
sir.
is fine. Hmm?
Yes, sir. Yes, sir.
Okay. Then okay. And right now I am going to what reflection is there. After that, what is there? Your projection. You
So
can
rotation.
rotation. Take rotation. Rotation map. Rotation by angle theta. Okay. I am telling the definition of what is the rotation operator. Okay. Rotation operator or rotation map. I am definition. Okay. And map or operator, whatever you can tell. An operator. Okay. That rotates each vectors. Okay. Is vector in R2. Here I'm talking about R2. So I'm taking R2. Okay. In R2 through a fixed angle theta is called a rotation operator. Okay. Yeah. So please tell me what is the matrix. Everyone are familiar with this polar coordinate or not?
Yes, sir.
Okay.
Yes, sir. R theta.
Yeah. Or and in Cartesian coordinate, okay, if I is this is your x, sorry, in Cartesian coordinate, if this is your x and I want to transform this one, okay, to another place, with a fixed angle theta, then what will be your after transformation, what will be your coordinate? Can you tell me? I am acting on this one and we'll get some image of this one. Okay, but what I am fixing the image. Okay, fixing the image means here I need only this transformation can be happen through an angle theta, fixed angle theta. Then what will be the image of this one under this transformation? Please tell me.
Sir, r cos theta,
No,
r sin
no.
theta, where
I am
r is under root x
I am
square.
in I need in Cartesian coordinate. Here I can't write properly. I'm right here. Okay. I think everyone are familiar with this y sin theta and x sin theta plus y cos theta. This is your transformations. I think everyone are have seen in your geometry classes.
Yes, sir.
Yeah, this is your transformations. Okay, through a fixed angle theta. Then what will be your matrix A?
Cos theta minus sin theta cos theta.
Cos theta minus sin theta cos theta. Okay, if I put theta equal to pi by 2, we will get Pesal transformations. Okay, what will be the Pesal transformation? What is the value of cos theta? Hey, cos pi by 2
0.
0, sin 1 1
So minus
0. This is your Pesal transform. This is the orthogonal transformation. Okay, so you will see in later. Okay, I am not going to that direction right now. This is one Pesal transformation. Remember these transformations. Okay, and projection map. What is the projection map? What is the matrix representation of projection map? This is the question. Yeah, projection we can take on x-axis or y-axis both. Okay, so if this is your point, take the projection on x-axis. Then what will get? X comma 0. Okay, on x-axis. What is the transformation? T of xy is goes to x comma 0. What is the matrix representation of this transformation? What is the matrix representation?
Sir, 1 0. Sir, 1 0 0 0.
1 0. Everyone are agree with this one? Risu?
Yes, sir, agree.
Okay. On y-axis? On y-axis?
Sir, 0 1 0 0.
Yeah, this is transformation is your x comma y equal to 0 comma y. You are getting a equal to 0 0. This one?
No. Yes, sir, correct.
Okay, right. Next we are going stretching. You are familiar with stretching? Stretching, S-T-R-E-C, stretching map. Okay, So taking along or alone or on, whatever, alone, yeah, is along x-axis. What do you mean by stretching map? Please tell me at first.
Sir, multiply it by a non-zero uh, scalar.
Yes, not full full coordinate. Only when I'm talking about along x-axis means only your x coordinate will multiply by some non-zero number, not y. Okay,
Okay,
understood?
sir.
Yeah. So suppose this is your x comma y. Okay. So we can stage this as twice, thrice. Okay, three times, two times, four times, alpha time. We can stage this first coordinate. So what we will get that time? Your x will be changed, y will be fixed. This, remember this one.
Alpha x comma y.
Yeah. So I'm right here. It will be better. Okay. So two, if it's multiplied by 2, we will get here 2 times 2x comma y. If you multiply by 3, we will get here 3x comma y. Okay, like that we'll get only this line. Okay, or this direction also we can get, no issue. If you multiply by minus something, we'll get in this direction, or if less than 1, then we'll get between this one, whatever. So stretching along x-axis, what is your map? T of x comma y goes to alpha x comma y. This is your map. What is the matrix representation of this map?
So alpha comma 0 0 comma 1.
Alpha 0 0 1. Yeah, fine. Along y-axis,
1 0 0.
yeah. So your transformation is x alpha y alpha non-zero. We are getting a is 1 0 0 alpha. That time we will stretch the y coordinate, so second coordinate multiply by alpha. Okay.
Okay,
Okay,
sir.
and the 1 minute. Try next. I will go through 1 2 example. Then I will finish. Okay. Okay. So find one linear transformation and corresponding matrix representations. Okay. Stretching stretching along y direction. Okay, and reflection with respect to y-axis. Yeah, these two will happen simultaneously. Okay, stretching along y direction and reflexing along with respect to y-axis. These two have to satisfy by one linear transformations simultaneously. Okay, means if this is your xy, okay, coordinate, then stretching along y direction means you have to multiply by some non-zero number your second coordinate. Okay, and as well reflexing reflection with respect to y-axis. What is the reflection in y-axis means? With respect to y-axis, reflection is like that here. Okay,
Minus x comma alpha y.
yes, correct. Minus x comma alpha y, but it will not be for reflection. I am getting this one. Okay, 1 minute. For reflection I am getting this one, minus x comma y. This is the point, and we need stretching along y direction, so we will get somewhere here minus x comma alpha y, where alpha is non-zero. Okay, or somewhere here or somewhere in this line we will get ultimately, or here maybe. Okay, is it okay or not? Please tell me. Could you understand what is the scenario is going on?
Yes, sir.
Okay, so at first I am taking the reflection, then we are taking stretching, or we can take at first stretching, then we can take reflection, no issue, whatever you want. Okay, if you first take stretching, then we'll go in this line, then I will take the reflections, then I will go come back in this directions. Okay, okay, so what is your map? Your map is x comma is goes to minus x alpha y. What is your matrix representation of this map?
So minus 1 0 0 alpha.
Minus 1 0 0 alpha. And then you can take stretching along x direction, reflection with respect to x axis, like that. Okay, you can combine both. Okay, 1 minute. Yeah, this is enough, I think. Yeah, this one, this few are enough, I think. You can combine projection and stretching, whatever you want. Okay, no issue. So this is your few interesting geometric map. Okay, this is few geometric interpretations, so the transformations. Okay, so do you have